In this lecture, I will give some concluding remark with the aim to help you with your project. Okay, so you now have got your data set and you did all the steps required in the theory. You checked if you needed to transform the data, you looked for trends, you looked for periodicities, you selected a good model, you determined a suitable model order that wasn't too high, wasn't too low, you checked the parameters and you checked the model residual, and yes, the model residual was white. So you go on and you look at your validation data. Remember, you divided your data into two sets, the modeling set, the validation set, and hopefully also a test set. So your prediction is done on the validation set. You're comparing your one-step prediction to your true data, the one that you stored in your validation set, to see whether you are able to use the model that you have constructed using the modeling set to predict data that you haven't seen before. That is your validation set. You want that residual to be white since you're doing a one-step prediction. If they are, that's fine, then you go on. If they're not, well, what do you do then? Well, you go back and try to tune your model. But as I will discuss shortly, there are also other things that you should keep in mind. So maybe your initial model isn't all that bad. Maybe there's just a need of fixing something. So what do you do then when your one-step prediction on the validation data seems to have a white residual? Well, first of all, you're happy because it seems that your model is actually pretty good. Then what you do is you stress the model. You try to predict further into the future. Say that you do a 4-step prediction, a 7-step prediction. How far can you predict ahead and it still makes sense? At some point it will break down. It will always happen. So there's no worry about it that if you try to make this 120 points prediction and it doesn't look that good, you shouldn't be too concerned. It will never work to do predictions like that. But a good model should probably be allowing you to do a, say, 4-step prediction reasonably well, maybe a 7-step prediction, maybe even more. If there are strong periodicities in the data, say that there are cycles of 24 hours, you should probably be able to predict one day ahead. But what if your predictions are pretty bad and you're looking at the residuals and they're clearly not behaving in the way you expect them to do? What should you do then? What should you be looking for? So let's look at some of the issues that might be worth considering then. First thing to check, are all your coefficients significant? Do you have values that are inside the confidence interval? Say something like this. So I have a parameter that has a value that is clearly insignificant compared to the confidence interval. You should omit that. That will hurt you. You want to remove it. It's only going to cause you troubles. So check using the present command to see whether there are coefficients that are clearly insignificant and then remove them and re-estimate the model. Remember, you always have to re-estimate the model when you make a change. Also, maybe you have some components that are just outside the confidence interval, so they are really, really weak. Maybe you can omit them and it still will work fine. Check, try, remove them, try it again. Also, maybe you have some coefficients that are just inside the confidence intervals, as though you have removed them, but it doesn't really work. What happens if you add those coefficients that are just inside? Does it work then? Of course, you might say then that these coefficients are statistically not different from zero. That is true. Of course, this is what we assume. But you should always remember that our results are asymptotic. We are using theoretical results based on the availability of infinitely many data points. You do not have infinitely many data points. That means that your confidence intervals and your tests are not all that reliable. You have to use your own judgment. If you have some component that is just inside, it maybe not. Maybe you should use it, maybe you shouldn't. However, it's pretty safe to say if you have something like this, it probably should go. I can't really see why that would be any reason to add a coefficient like that. But keep an eye on the confidence intervals and check your values. And if you're really close, just inside, just outside, be a bit suspicious about the decisions you make about those coefficients. Next, you might have differentiated your data because that seemed to make sense. You had a trend and so you differentiated the data. And that's a great idea, of course. But then when you look at your PACF, you still have some dependency at lag 1 that you can't really get rid of. The first thing to do would be to try to use a C1 coefficient. Often when you add an A coefficient, say an AP coefficient, you might need to add also a CP coefficient to counter that effect. It's quite common. So adding an A3 coefficient doesn't mean that you should add a C3 coefficient, but you might check if that is also something that's needed. The other alternative is that instead of using the differentiation, you move over and use a 1 minus A1 set to the minus 1 instead, and you then estimate the A1 coefficient. Maybe it should be less than 1. Maybe this is too strong to use a A1 coefficient that is 1, which is what the differentiation is. So maybe you should try to use it a little lower value. So you add that into your AR part of your model, and then you estimate that coefficient as well and see if it works better. Remember, you are adding one coefficient, so of course that is not good. But on the other hand, you're giving your model more flexibility, and that probably helps you too. Estimating a couple of more parameters is not in itself going to hurt you all that much. Of course, you try to estimate as few parameters as you can, but it's not going to be critical by adding just a few more. Try it out, see if that helps you. Quite common is also that your periodicities are not perfect. Say that spring is in the air. That means that the day cycle is maybe not perfectly 24 hours. Maybe it is just 23.8 or something like that. What do you do then? Well, then instead of having just say 24 here, you add a 23 and a 25. So if you estimate these coefficients, you might then find out that this should be there, this should be there, and this is really, really small, so you cut there, and then you just keep these two. Or maybe you just keep these two, depending on if it's spring in the air or fall is coming on. But the idea here is that you allow for coefficients that are not perfectly on the grid. So your periodicity is not required to be perfect. So you add one on each side to try to determine if that is a good model. Maybe you will need all three to capture that periodicity well. There is an example on speech coding on this in the book, so have a look at that. Next, don't oversimplify your model. It's very unlikely that you can get away with using an AR3. Every year there's someone who tries just because they want to use the recursive least squares instead of actually implementing their Kalman filter, or they have problems getting their Kalman filter to work. Don't do that. You need your Kalman filter to get it to work well. It's a safe bet to say that an AR model will not be sufficient for the data we're looking at. You will need an ARMA, so you will not be able to use the RLS. Try to find that bug in the Kalman code instead. Another very common thing is that you get predictions that are lower than you expect. Something like this, and you can't really make sense of it because your model seems to be great. The most common error here is that you have forgotten to add the predicted future inputs. Remember, you have to construct your estimates by adding predictions of your future residuals. You cannot do that, you put them to 0, but you can predict the future inputs, and you have to do that. And if you do not do that, you'll get exactly this error. So if you get a prediction that seems right, but it's just too low, check if you did add that f hat component with the predicted input. So another common reason for frustration is that you work and work and work on your residual, but there's still dependencies in them, and whatever you do, you cannot get rid of them. This can be because your ARMA model that you are using is just not good enough. You cannot model what you are seeing with a stationary model. You might need to allow those coefficients to change using a recursive formulation to allow you to model something that is a season that is changing, for instance. So instead of wasting too much time in trying to get that model to work perfectly, when you have a model that seems to be reasonably good, go and try and see if you can make it better by using the recursive model. And if you can, then that is likely the reason, and you just have to live with that. Maybe you can use the insights you get from the recursive implementation to improve it a little bit, or maybe you just have to live with it being not perfect. And this one is super important. You should always remember to compare your results with a naive predictor. Say that I am predicting the temperature 1 hour from now, and I build this super fancy model, and I try to predict it. If my error in that prediction in my super fancy model is not better than if I predicted the future temperature by just using the current temperature, my model is not worth anything. So I want to construct a naive, simplistic predictor. It shouldn't be stupid, but it shouldn't be very refined either. So for instance, say that I'm trying to predict the temperature 1 hour from now. I use the current temperature. Say that I want to predict the temperature 7 hours from now. Maybe what I should be using is the temperature yesterday at that time point. Those are reasonable guesses. They shouldn't be completely off. And your model needs to be better than that. If it is not better than that, your model is not worth anything, and you should go back to redo it. You always need to remember to keep your naive predictor there. You have to have a naive way of estimating things and compare to that. And you need to be better at it. It's very, very important. So remember to do this. Quite often, people are transforming the data when they don't need to do that. So start by looking at your Box-Cox curve and say that it looks something like this. So it seems to be relatively flat from the point that suggests that you should use a log to the one actual true peak which says that you should take the power of 87 to your data. Obviously, you should not take the power to 87 of your data. It's just going to corrupt everything. So look at the Box-Cox plot. The point where the peak is has to be significantly higher for you to choose that one. Otherwise, there might not be a value in doing that transformation. And even if so, you might not want to do that transformation anyway. When looking at the data to determine the transformation, you should look at the entire data set. So different from what I have been saying all through before, when I only looked at the modeling data set, when you look for transformations, you compare the entire data set you have. And the reason for this is very simple. Say that I'm looking at the temperature of the seasons. It seems to grow, right? But that is because it's spring. Then there will be summer. Then there will be fall. Does it make sense to expect a growing tendency to continue into the fall? No, it doesn't make any sense. So maybe it doesn't make any sense for me to use a transformation on that kind of data set either. Be careful with making transformations, and if you are making transformations, be careful to make any other transformation than the log, because that seems to be the only thing that is reasonable in most cases. That is not to say that you shouldn't use a transformation. So maybe you want to use that transformation to make your data look a little bit more Gaussian. Taking the transformation of your data will make it more Gaussian. Maybe that is exactly what you need to make it work. Maybe there is a trend that you need to capture using this. Maybe not. Be careful with it and evaluate carefully if you should add it or not. I cannot stress this one enough. Always, you should create a simulation model of your data, simulate the data, test your estimator and your predictor to see that it works. If I simulate 10,000 data points, I should get almost perfect estimates of my model parameters if it's a reasonable model. If I use the true parameter to predict my model k-steps ahead, it should work beautifully if it is the true model that I'm trying to predict. If it's just slightly wrong, it should still work reasonably well. Make sure that this is true, otherwise there's a bug in your code. It is so much easier to find that bug if you use simulated data when you know the true answer, than if you look at some data that you have measured where there is no true answer. Then when you know that you can trust your code, you move over to look at the actual data, and then you can trust the results you're seeing. But before that, you cannot really trust them, and so you should always simulate some data and check with that. Then there's the question of outliers. Sometimes you can just see it, they're obvious, there's something sticking out like this. It shouldn't be there, and you can sort of visually see it, you need to deal with it. Sometimes it is quite difficult to see that there's something going on, and there's subtle outliers such that there's just a structural change going on at some point. Those are much harder to detect. You should be suspicious of real data. Almost all forms of real data will contain outliers, so you should search for it and see, particularly before you start, if the data set that you're looking at have obvious outliers, and then take care of them. Compute the TACF, see if it differs significantly from the ACF, and then that's a very good indication that there is a problem. You might don't need to do it, but it's very wise to check. Also remember that all the results we have discussed so far are only valid asymptotically. That means that the plus minus 2 over square root over n is an asymptotic result when n is very, very large and the data is perfectly Gaussian distributed. It's never going to be perfectly Gaussian distributed, and it's not ever going to be large enough for that approximation to be good enough. So you should always be skeptical to the results. All the results we have are tools. They are tools, they are reasonable tools, they make sense, but they're imperfect, and you should be aware of that they're imperfect, and you do not trust them fully. If you use a KiKit to estimate the model order, that might be an indication what is a reasonable model order, but it's not going to be something you can rely on. An important part of this course is to know when you can rely and how much you can rely on the different tools that we have learned, and basically be very skeptical to these tools. It is often quite wise to plot the ACF without lag 0. The reason for that is that if I plot it like this, you can see it's quite difficult to see whether this is actually a significant component or is this a significant component. They all look very small to me, right? Because you compare it to a 1, because you had a quite large data set and your confidence interval is very slow. The ACF function has an option that you can omit the first lag when you plot it, and then you get a plot like this instead, where it's much clearer to see that this is something that you need to deal with. It's a good advice, especially when you hand in a plot to someone. If you hand in a plot like this, it is very difficult for the one who's grading you to see whether that is significant or not, right? So try to hand in a plot like this to me. Next, always do your predictions and plots in the correct domain. If I get a plot like this, what does it really tell me? I have differentiated and transformed data that has some form of weird behavior. I cannot really make any conclusions. You must go back to the original domain. If your measurements are in degrees Celsius, your predictions should be in degrees Celsius. Otherwise, they make no sense. Always go back to the original domain before you present it. So you must make sure that this is happening. Otherwise, I cannot give you marks for those predictions. You should also plot those predictions to see, do they make sense? Say that your validation data looks like this and your predictions are looking like this. There is something wrong, even though that might not be visible in your ACF and the PACF because that is hidden because of the non-stationary behavior. Plot them and see that you get something that is reasonable. Also be aware that when you create a model without an input and it works fine, and then you add an input, you need to remove your original model and try to explain everything that you see using that input. Otherwise, if you just add the input and you're using the old model, that of course will work great without that input. You don't use that input because your model is taking care of it. You need to remove the earlier model, build a new model that exploits the input as much as you can, then you start modeling whatever cannot be modeled. Be careful when you use fancy MATLAB commands. They are great, they are exceedingly well implemented, and they can do wonders for you, but you have to know what they're doing. Because if you call them and you don't know what they're doing, they might do something different from you expect. It's very, very common error that you are using a fancy function, but you're using it wrong, and so your results are just making no sense whatsoever. My normal recommendation is that you try to use very few fancy functions. In the initial stage, you use filter, for instance, you get a result, and then you add more fancy functions using forward, backward averaging, and so forth, when you know that you have something that is reasonably working and checking that you did it right. Simulate your data again, check that your code is right. So what do I do if I have more than one input? Say that I'm modeling the energy consumption of a city and I have the temperature and the wind and the humidity data collected in this city. The first thing to do is to determine which of the data set is most strongly correlated with the energy consumption, probably the temperature in this case. Then I build the model with using only the temperature as input. Then I remove that and look at the residual. Then I try to see which of the other input is now most strongly correlated to what is left. Then I build a model, you try to explain that of what is left, and so forth. Remember, you cannot get something that works perfectly when you are modeling reality with 5 parameters or 10 parameters or something like that. It's not ever going to be perfect, but it can be good enough. And if it's good enough, you should be happy and let it be.